Hi! Well, thanks for taking the practice exam. We're going to quickly go through the problems in a couple of minutes. But before we do, I just want to give a couple pieces of advice. This shouldn't surprise you. I often give advice. Occasionally it has been good. So, when you're taking the test, pay attention and read it carefully. There's a tendency sometimes to not pay attention, and you might notice that we maybe have a slightly different order that we write things in than normally, or maybe there's something which is a multiple selection problem and there might be more than one correct answer. Read the prompts carefully. Related to that is work to eliminate options. A multiple choice test is different than the kind of test we've done in the past. You don't have to show all your steps. You just have to do enough to be able to get to an answer. And one way to get to an answer is to say, well, let me eliminate other possibilities. And so if you can work to eliminate the other possibilities, that helps. There's a lot of time to take the test. We recommend you start early if possible and get it done. I know it looks like it says get it cloned, but that doesn't make any sense. No, get it done. And just don't have this hanging over you all day. You should just get it out of the way and be free. And don't panic. And I understand the test is stressful. That's why we want you to start it early. So if you need to take a break, get up from your computer and walk around for a couple minutes, you can do it. If you need to go scream into a pillow, get a drink of water, use the restroom, okay, that's fine. Don't panic. And remember, we do love you. Now, that isn't to say we're not going to challenge you, because we always challenge the people that we love. You might have experienced that in the last couple of weeks, that some of the biggest challenges have come from your loved ones. But we want you to succeed. We're not going to punish you. See, there's a difference between being challenged and being punished. We're here to challenge you. And that means that we believe in fairness. We're going to give you a fair test, and we're going to let you have an opportunity to demonstrate what you've learned. And we hope that you've learned something. All right, well, with that out of the way, we can begin. The first problem. And I will say, I'm not going to try to answer every possible detail. The goal is not to teach the class here. The goal is just to go through and do some problems and give you some idea. So we're going to go at a little bit of a faster pace than what we might normally do during a review. So, at which value of x does the curve x squared plus y cubed equal 2 have a vertical tangent line? Now, this kind of relationship here, it doesn't really have y as a function of x or x as a function of y. So this would probably be the best thing to do, is to think in implicit when we see something where there's not one function clearly in terms of the other. So remember, when you think of implicit, the way we do it is we have our little thought bubble and we think, well, y is some function of x, we just don't know what it is. So in our case, we have taking the derivative with respect to x, 2x plus 3y squared y prime equals 0. So I took the derivative of both sides with respect to x. Or y prime would be equal to minus 2x divided by 3y squared. All right, so far so good. Now, when do we have a vertical tangent line? Well, vertical tangent line would be something where our tangent line would be something straight up and down. So, what's the slope? Well, the slope is undefined. So we're looking for where our slope is undefined. So if I'm looking for where something is undefined, I'd really look and say, when is the denominator 0? Then I might say, well, what about if it was 0 over 0? Well, if it was 0 over 0, that would leave us to 0 plus 0 equals 2. Impossible. So we want to know, when does y equal 0? Okay, well, we have y equals 0. So x squared plus 0 equals 2, which means x is the square root of 2. But wait, plus or minus. Good. So now we know our answer, plus the square root of 2 and minus the square root of 2. And notice this is a select all that apply, which means there might be more than one. And there is more than one. And those are our answers. All right. Number 2. A rectangular sheet with perimeter 36 centimeters and dimensions x centimeters by y centimeters is to be revolved around one of the sides of length y to sweep out a cylinder. This is kind of a strange thing, but okay. What's the basic idea? I have x, and I have y, and now we're going to spin. And as you spin, you get a shape. That forms a cylinder. All right, so there we go. There's our cylinder. Now, determine the values of x and y that give the cylinder of maximum volume. Okay, well, what are we actually looking for? From the following statement, select all which must be true. Oh, okay. So we've got to figure out which statements are true. So let's see. What do we have? Well, VV is volume of the cylinder. V equals pi x squared 36 minus x is one of the two equations we want to optimize. Maybe. Well, let's think about our volume. Well, we'd have that. So what do we know? Well, the radius is the x. Okay, so that's looking promising. So we get pi x squared. What about the height? Well, the height is y. All right, well, that doesn't match that. But wait, hold on. Remember, if we're going to do an optimization problem, we have to get things down to one variable. What's our other equation? Well, what haven't we written down? Whenever you see a number, you should always ask, is it going to be used? In this case, there's this number 36, so we should probably use that. And where does 36 come in? Well, if I add up the lengths of the sides, which is x, x, y, y, that's the perimeter, because it says perimeter. 2x plus 2y equals 36, so x plus y equals 36 divided by 2, which is 18, which means that y is 18 minus x. So it's pi x squared times 18 minus x, not 36. So this is false. All right, good. Now we know. Part B. Volume is pi x squared times 18 minus x. It's one of the two equations we want to optimize. Yeah, we did that one. True. Okay, good. The maximum volume occurs when x equals 12 and y equals 6. Okay, so that's about the optimization. So, well, now that we have our equation of one variable, take the derivative, but, well, let's first multiply. So multiply this through, you'll get 18 pi x squared minus pi x cubed. We actually could just throw out the pi because it's common to both. Now, that's our v. We take our v prime, 36 pi x minus 3 pi x squared. We can factor a 3 pi x out, and that leaves us with 12 minus x. Now, clearly x equals 0. That would be no width at all. Not going to happen. Okay, so we know it's not x equals 0. So we say, aha, that tells us that x equals 12. And if x equals 12, y is 18 minus 12, which is 6. 12 and 6, that's true. All right, good. Now, the maximum volume is 860 pi centimeters cubed, or the maximum volume is 864 pi centimeters cubed. Well, they both can't be true. They might both be false. That's possible. So how do we figure that out? Well, we got to do the math. So what's the math say? Well, we know what our measurements are, right? So we have x is 12. So the volume, whoa, we're in a space. You can use lots of scratch paper, by the way, when you're taking the test. Volume is pi times 12 squared times 18 minus 12, which is 6. Now, that's equal to pi. 12 squared, kind of gross. A little bit of math humor, right? A dozen is a gross? Yeah? No? All right. Anyways, 144 times 6 definitely is an 860, so that's clearly out. No way I can get to 860. It does turn out, you can use a calculator. If you take 144 times 6, well, think of it as pieces. 6 times 100, that's 600. So we'll do some computations here. 6 times 40 is 240. 6 times 4 is 24. And if we add that up, we'll get 8, 6, 4, and then there's a pi. So this is, in fact, true. So that's our pattern. False, true, true, false, true. Cool. A great way to compress many questions into a single one question. Woohoo! Efficiency. All right, number 3. A 10-foot ladder is leaning up against a wall. Ladders often do that. And the bottom of the ladder is currently 6 feet away from the wall and sliding away from the lattice at a rate of 2 feet per minute. So we've got our ladder here. And again, your picture doesn't have to be super precise. You just need to draw something to give you your idea. So there's 10. Now this distance, what do we know? Well, it's currently at 6 and it's increasing 2 feet per minute. Sorry, there we go. All right, so that's what we know. So I gotta say, by the way, ladders sound very unsafe if you take calculus classes. They're always moving. That's a very, somebody should fix that. All right, so, that's x. Okay, so what we're told is that x equals 6, and then this 2 feet per minute is another way to say dx dt equals 2. Because x is the distance from the bottom of the ladder to the wall, so this part is x, and y is over here. Now, what are we after? Well, our variables are related to each other by x squared plus y squared equals 100. Well, it's a triangle. X squared plus y. Yeah, it's a right triangle. That's right. It's not just any kind of triangle. It's the right kind. So good, we're going to take that one. We know dx dy equals 2 feet per minute. Careful, they're trying to trick us. That's the dx dt, not dx dy. Tricky. That's why we want to pay attention. False. Part C. In order to know how quickly the ladder is moving down the wall, we should set our derivative equal to 0. Well, that's kind of vague. Derivative of what? Well, that's if we have really a function of one variable and we were trying to find the min or the max. See, saying derivative equal to 0, that's optimization. Are we in an optimization mode? And the answer is no, we're not really in an optimization mode. What we have is equations which are related to each other, and we have a rate. So it's a relation of rates, or related rates. No optimization. This is false. Both x and y are functions of t. Yes, that's why we think of related rates. True. Now, the ladder is moving down the wall at a rate of -3/2 feet per minute. Well, let's take our derivative with respect to t. So we get 2x dx dt plus 2y dy dt. Derivative of 100 is 0. It's a constant. All right, the 2's, we can knock those out. We know what x is 6. We know what dx dt is 2. We don't know what y is, but wait. It's a right triangle, right? So let's see. What would that be? 36 plus y squared equals 100. Because I'm just putting in what we know. Y squared equals 64. So let's see that. Y equals 8. Okay, 8. 8 dy dt. Okay, so we'll move the 12 across. We get 8 dy dt equals -12. Good, because it should be moving down. Divide both sides by 8. And if we take -12 over 8, well, they both have a 4 in common. And that's the same as -3 over 2. Good. And we should also just check the units. They might be trying to trick us. Feet per second. No. It's feet per minute. Consistent. So this is also true. All right, good. Woohoo! Fun problems. Don't worry. They're not going to be all which are true. We're going to mix up a little bit. Here's one. Evaluate the limit as x goes to 5 of x squared minus 8x plus 15. Now, of course, you can do this in a couple of different ways. Now, what's one way to do it? Well, one way to do it is to say, first off, plug in 5. What do you get? 25 minus 40 plus 15 is 0. Downstairs, you get 0. Okay, so 0 over 0, we like to say, Well, maybe you don't like to say it, but I like to say it. No, l'hôpital, mon ami, it has been too long. All right, so if we apply l'hôpital, what do we get? Limit as x goes to 5, derivative of the top, 2x minus 8, derivative of 1 over 2x. Well, got to be careful there. What's the derivative of 1 over 2x? It's negative 1 over 2x squared, right? Because how do you think of that? Think of it as really a half times x to the minus 1. So that's where the minus comes from, because you bring the minus 1 down, and it becomes x squared. Now, plug in 5. 10 minus 8 divided by minus 1 over 2 times 25. That's really 50, and we should bring it upstairs. So 10 minus 8 is 2 times negative 50, which is negative 100. Done. Now I said there's lots of ways you can do this. Here's another thing you could do. You could say, hey, this just looks like algebra, and I love algebra. You may not be saying that at this point in the semester, but boy, you know, can you just pretend, just for me, for old time's sake, that you're like, oh, Steve, we love algebra. We'll always love it. Oh, thank you. It makes me feel better. Okay, you could have done the following. You could say, well, that's going to factor. We know it factors because 5 is a root. So it factors as x minus 5, x minus 3. Downstairs, well, you could pull out common denominator. What would that be? Well, 1 over would be 10x, right? What would be left in the first term? Well, it would be 5. And what would be left in the second term? It would be, what would it be? Right. So what do you have to multiply 1 over 10x by to get 1/10 is x. And you say, oh, wow, look, if I pull the negative out as well, I get negative 5 plus x. Those cancel. So it's really x minus 3 divided by negative 1 over 10x. Or it's really negative, because I can just move the negative upstairs, x minus 3 times 10x, because I can just flip that up, which is really, now I go to 5, so that goes to minus 5 minus 3 times 10 times 5, which is, believe it or not, still negative 100. Cool, we got it again. Now, you're allowed to use a calculator. Is there a calculator way to do it? Yeah, here's a calculator way to do it. Plug in, say, 5.01 to the expression, and that's going to be close to one of these numbers, because these numbers are far apart from each other, and it's going to turn out to be really close to negative 100, and therefore that's going to be what you want. Now, you might say, well, which one do I do for credit? And the answer is it doesn't matter, because we'll never see your work. The one you should do is the one that you are confident you can get correct. That's what you should always do. You should do what you're going to be like, there is no way I'm going to miss points on this because I'm awesome and I love being awesome. Yeah, dude, totally be awesome. Okay, that's not sexist because I said dude. Dude and dudettes, totally be awesome. There we go. That's right. I'm woke. Okay, we want to find the derivative of an integral of sine of 3t e to the t dt. Which of the following would be the best first step? Well, find the antiderivative of sine 3t e to the t. I'm going to go with a hard pass because that sounds hard. How do I know? Well, because we don't have the tools to do it. You might say, are we ever going to have the tools to do it? Yes, we will. When Calc 2, all the happy days of Calc 2. But that's for next semester. Okay, use the fundamental theorem of calculus. Oh, right, because there's a derivative and an integral. The fundamental theorem of calculus says we can do stuff when we're taking derivative of integral. Oh, this is cool. This is a good idea. Now, is it the best idea? Well, let's see what our choices are. Well, guess and check. Yeah. Look, guess and check, great for diffie Q, but we're not in diffie Q. So that's not us. We don't want to do a guess and check because you know, could be guess wrong. That's not the best way to start. Sketch the curve to calculate how the area under the curve is changing. Well, that's basically like trying to do an antiderivative. Sounds hard again. It looks like there's only one good idea. So that's got to be our best idea. In fact, it is our best idea because, the derivative of the integral from some constant x of f of t dt is really just f of x. That's a freebie if you know the fundamental theorem of calculus. And remember, as the saying goes, you can't do the fundamental theorem of calculus without having fun. That's right. Now you're probably thinking, Steve, I think you got that wrong. You can't use the fundamental theorem of calculus without going mental. Well, I like the fun interpretation because I think life should be fun. Don't you? It's a much better way to approach life. Number 6. Consider the function f of x equals absolute value of 2 sine x, and that's this dotted line here, and g of x, which is negative sine x, that's this solid line. Determine the area between f of x and g of x on the interval, 0 to 2 pi. So that's 0, there's 2 pi. So that's this piece right here. Now, all right, well, The tricky thing is that the absolute value, whenever you have absolute values involved, it just makes life more interesting. So let's see how we can do this. Well, really what we should say is absolute value of 2 sine of x depends on where you're at. See, initially sine is positive, so the absolute value does nothing. So that's 2 sine of x if we're between 0 and pi, but after pi, between pi and 2 pi, it would normally be down here, so the absolute value would flip the sign, minus 2 sine x between pi and 2 pi. So, what would happen? Well, if we're looking for the area, you take top minus bottom. So it's integral 0 to 2 pi of 2 sine of x minus sine of x dx. But whenever you have absolute value, break it up. So 0 to pi, well, what happens? Well, that'll be just 2 sine of x minus makes a plus, so that'll be 3 sine of x. And then we're going to add to that integral pi to 2 pi of what? Well, this would be minus 2 plus, so minus sine of x dx. Those aren't too hard to do, and we could do it that way, but let's just say, hey, we're in a test, let's have fun, and say, wow, hey, look at the picture. This piece here matches that piece there. And it's like, whoa, cool. So, if I think about moving this to there, it's just like I have this double bump. And I say, well, wait, it's a double bump. And so, an alternative could be, let me just find the area of one bump. This thing, if I could just find that area and times it by 2, then I'll be good. I'll have the answer. So, here's my computation. I'm going to take 2 times integral from 0 to pi of 2 sine x. Because this part of the bump is coming from 2 sine x. Well, okay, so that's really 4. Integral of sine, well, we know that. That's negative cosine. Okay, cool. Now, evaluate that from 0 to pi. What does that become? Well, minus cosine of pi. Cosine of pi is negative 1. So that's 4 minus 1 is plus 1. Subtract cosine of 0 is 1. So minus a minus 1. So really 4 times 2, which is 8. That's the answer. Ha-ha! Woohoo! All right. So consider f of x equals minus 2 arctangent of x. All right. Well, what are we looking for? For what x does the second derivative equal 1? Now, what is this testing on us? It's testing us on the derivative of arctangent. So we know that f prime of x derivative of arctangent is, well, the minus 2 comes along, 1 over 1 plus x squared. Now, we're going to take another derivative, so let's rewrite this in a more convenient way. Say 1 plus x squared to the minus 1 power. So our second derivative would be what? Well, minus 2 stays there. Minus 1 comes down. 1 plus x squared to the minus 2. And now multiply by derivative of the inside, 2x. So that would be 4x over 1 plus x squared squared. Now, we want to know, when does this equal 1? Well, that sounds like a lot of work, because we have to solve something hard, except we have options. Let's use our options. Is it 0? No, right? Because 4 times 0, out. Is it 1? 4 times 1, that's 4. 1 plus 1, 2 squared. Oh, it's 1. So this works. We should double check the rest, just to be careful, right? 4 times 2 is 8. And downstairs it would be 1 plus 4, that's 5. 8 25ths, that's not 1. 16 over 17 squared, no way, that's 1. So yeah, it's 1. See, we didn't actually have to do the computation. We said, okay, we got to a certain point, let's check our answer. Now, on a side note, because I don't think it's going to come up in the rest of the problems, this is related to one thing that you may want to be comfortable with, and that is that the derivative of inverses. So just remember, arctangent, that's the inverse trig. You should know your derivative of inverses in general, namely it's 1 over f prime of f inverse of x. So just make sure you know what to do in general. Okay, take the derivative of f of x is 3 to the x cubed times e to the x over x squared. Now, there's sort of two options here. One option is quotient rule, and well, I should say quotient rule plus patience. So the reason I say patience is it's going to take a while to work it out. Well, we have time. There's no time limit on the exam. But the other option is actually logarithmic differentiation. And so I am, well, I mean, I can do it both ways, but there we go. Got it to fit. I'm going to go for logarithmic differentiation just because I think it's such a cool idea. Now, when is it a clue to use logarithmic differentiation? The answer is if you have a bunch of stuff multiplying or dividing together. That's a good sign. It's a must if you have the following: a function to a function. In that case, no choice at all. Now this one, choices. But yeah, we have to work our way through and see what happens. Now, depending upon what you see, you can actually eliminate some things pretty quickly. I claim that you'll see there's this derivative of 3 to the power x cubed. If you're familiar with that, that says at some point I have to take the derivative of 3 to the power x cubed. And if you remember your rules, the derivative of, say, constant to the x is constant to the x log c. Since there's a 3 here, that says I'd have to have a log 3. So anything without a log 3 gets knocked out. So we can eliminate some options really quick if we say we know certain things have to happen. All right, well, what's the rest going to be? Well, let's do it. Now, logarithmic differentiation says what? It says the derivative of f of x is the same as f of x times the derivative of the natural log of f of x. Now, you'll notice in the two cases remaining, here, these are our f of x terms. So, what we really want to do is take the derivative of the natural log of f of x and see which one ends up here. All right, so the derivative of the natural log of 3 to the x cubed e to the x over x squared. Now this gives us a chance to really flex our algebra skills. See, logarithmic differentiation is not a differentiation technique. It's a logarithm application to simplify the function. So what happens is things multiplying in the top, that becomes addition, and things multiplying in the denominator becomes subtraction. So log 3x cubed plus log of e to the x minus log of x squared. Of course, exponents come down. That's in the power of, well, I shouldn't say power, but a property. X cubed log 3 plus e to the x times log of e, which is just 1, minus 2 log x. Take our derivative. Derivative of x cubed, 3x squared log 3. Well, it's here, not there, so we're done. Let's just check the rest. E to the x, yep, that's good. 2 natural log x, 2 times 1 over x. And yeah, the rest of it matches as well. All right, and so there's our answer. B. Woohoo! Done. All right. Number 9. Let f of x be a differentiable function on a closed and bounded interval. From the following statements, select all which are true. And when we're talking about which are true, we're talking must be true. Must be true. Okay. All critical points of f of x are either a minimum value or a maximum value. So this is the statement. If you're a critical point, you're a min or a max. Is that true? And can you think of any case where it's not true? Well, I can think of one. X cubed. That's a critical point, but it's not a min or a max. So this first one is false. Remember, if you're asking whether something is true, we mean always true. So yeah, that's not always true. Suppose f of a equals f of b. Using the mean value theorem, we know there is a point, critical point of f of x, okay, at x equals c equals b minus a over 2. Now, where's a critical point? Well, the critical point would be where the derivative equals 0. It is true by the mean value theorem that because the endpoints have the same value, that means the average rate of change is 0. So the mean value theorem says there has to be some place where the derivative equals 0. But notice it goes a step further. See, if it just stopped there and said, aha, there has to be a critical point, that's a true statement. But then I said, and here's where it's at. It's halfway there. That's not always the case. You could create a function. Here's a, here's b. And you could say, well, look, it's going to do something like this. Okay. Now notice, where's our critical point? It's there. It's not halfway. It's somewhere in between. But somewhere in between doesn't mean halfway in between. So, false. My gosh, that's crazy. Is there anything true? Well, we still have 2 more to go, right? There exists a global maximum and global minimum value of f of x. Well, let's see. We know it's differentiable, and it's closed and bounded. And so, this is true. And this is sort of the extreme value theorem. And it says that as long as you have a nice function, it doesn't even have to be differentiable. See, differentiable, this implies continuous. So as long as you have a continuous function on a closed bounded interval, then you have to have a global max and a global min. And that's just one of our basic tools. In fact, it's an amazing tool, simple to state, hard to prove, as many things are. Which comes to our last one. Okay, boundary points must always be either a maximum or a minimum. Well, that says, okay, so I have a boundary point. So here's my boundary point. And then it says, look, this point, let's say, here's your a. As your function goes out, it's either a min or a max. Well, seems true in this case, right? But remember, is it always true? Is it the case, well, maybe, it could go down. All right. But is it the case that as I move out from A, that I'm always going to go up or that I'm always going to go down? Now, it sounds like the answer has to be yes, right? Because you have to be doing one or the other. But remember, think like a mathematician. And this one, I'll let you in on a little secret. I put this one in here just for fun. I hope the TAs get this. We'll see. I don't know if they're going to watch this part. What do you think? Is it true or false? It's false. What? Oh my gosh. I can't believe it. Or can I? Yes, I can. Now, you might say, but how is that possible? And the reason is, you might say, look, it's not going to be a max or a min. And see, the reason that the boundary is kind of curious is you only go off to one side. See, if you're not on the boundary, you have two sides to go off of. So when you're only going off to one side, it feels like you either have to be going up or you have to be going down. They might say, aha, Steve, it's because it's flat, right? Well, no. Actually, if you're flat, you're still a max or a min. But what you can do is you can do something like this, where you oscillate, but you just start oscillating more and more frequently, but the oscillations get smaller and smaller. So an example of this, you can have f of x be the following. X sine 1 over x, and this is for 0 up to 1, actually not including 0 because it's undefined, and 0 for x equals 0. And so the thing is, as you're coming into here, the boundary, you're keep moving up and down, above 0, below 0, above 0, below 0. And so it's not a max or a min at 0. Now, this one is extra tricky. And so we would never put this one on the actual exam. So it's a great one for the practice, though. It's a great one to, like, stump your TA with. Oh, it's so fun. Yeah, this one's good. I like this one. I like this one. This is fun. I hope you're having fun. Okay, next one, number 10. When solving the integral of cosine x over 2 minus cosine squared x dx using substitution, you get to the integral of 1 over u squared plus 1 du. Which of the following was the choice for you? So there was a substitution made. The question is, what substitution was it? That's an interesting question. Now, there's a couple ways you can approach this. Some ways are better than others, but oftentimes I kind of sort of like to compare. See, like here, the numerator, I've got a 1 du, and here, kind of like a cosine x dx. So it feels to me like cosine of x dx became du. Now, that's not a guarantee, but it feels that way, and so we start to think, okay, what has a derivative of cosine? Well, we can rule out u equals x, because if you just do u equals x, you'll end up with a cosine u, 2 minus cosine squared u du. It doesn't change anything. Okay, so that's not it. Derivative of cosine is negative sine. Derivative of cosine squared x, really crazy. Derivative of sine of x, ooh, now that's promising, that's promising. See, here, derivative of sine of x is cosine of x. Now, that doesn't mean for sure that was our substitution, but let's think about it. So what do we have? Well, one way we can think about it is say, all right, if that was our u, so we would have du equals cosine of x dx. All right, that's good. How does this 2 minus cosine squared x become u squared plus 1? Well, now we say, oh wait, 2 minus cosine squared. That's the same as, I want to rewrite this in terms of sine, because if we're doing a substitution, we want to make a change. I got to be careful not to say a change in sign, because that could be misinterpreted. And if it's one thing we don't want to do is be misinterpreted. I see there's a plus 1, so I'm just going to pull off a single plus 1, and then a 1 minus cosine squared, and hopefully this is starting to ring some bells. 1 minus cosine squared is sine squared. So, sine, make that u squared. Aha! Which means it does work. So that was our substitution. So the answer is C. Cool. Cool. Okay, number 11. The graph shown below is h prime of x, the derivative of h of x. I can tell it's the derivative because it tells me right there it's the derivative. How many inflection points does the graph have between -6 to 7? Okay, so what's an inflection point? Well, an inflection point is change in concavity. Now you might say, aha, so something like this, right? Go concave up, concave down. No. Be careful. See, that would be if we were given the graph of h of x. That would be what an inflection point is. This is h prime. So we've got to make sure we understand it. So an inflection point, how does it show up for h prime? Well, that would be concavity changes. Now, what it means is that you go from f prime positive to f prime negative. Or you go from f prime negative to f prime positive. Because when we're talking, let me be really careful here. That's not, I want to make sure I get this right. Because when I mean f prime positive, we want to change from f prime increasing to f prime decreasing. That's what I meant. And here we want to change from f prime decreasing to f prime increasing. Because when we're talking about concavity, concavity is saying how is the derivative increasing or decreasing. Okay, well this might sound familiar. It says I'm increasing and decreasing, or I'm decreasing and increasing, which means what we're looking for is we're looking for our mins and maxes. Those are what we're going to find our inflection points. Why? Well, think about it. Let's grab them. 1, 2, 2, 2, 2. These are our mins and maxes. Because what's happening is, I pick here. Before that, my derivative is going up. After that, my derivative is going down. So I'm concave up, I'm concave down. Therefore, I'm at an inflection point. So I just have to count how many mins and maxes do I have. Well, 1, 2, 3, 4, 5. And that's the answer. 5. Now, this one's not so hard if you know what to look for. But if you don't know what to look for, it can be challenging. So this is sort of a, do you understand what to look for? So it's good to know. Good to know. All right. So, number 12. Ooh, this will be the halfway point once we get this one done. So, given the second derivative is x squared minus 6x plus 5, divided by e to the power 8x squared minus 9 times x squared minus 1, which of the following points can be a local maximum of f of x? Ooh, that's interesting. Now, you might notice, does anything factor? Because, it's good to sort of do a quick spot check. Of course, x squared minus 1 can. X squared minus 1 is the same as x minus 1, x plus 1. How about x squared minus 6x plus 5? Well, yeah, that actually factors. X minus 1, x minus 5. So if you see that, the x minus 1s will cancel. So you can simplify to say, look, it's x minus 5 over e to the 8x squared minus 9 times x plus 1. Cool, 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 cool. Now remember, this is our second derivative. Okay. Now, next question. What's our key word here? Now, I know we're all thinking it, and the key word is not partial credit in that, I missed the chance to get partial credit. So it's not about partial credit. So what's the key word here? It's actually kind of a small word. It's this word right here. Can. So we're not going to show that any of these are local maximums or local minimums. But notice we have the second derivative. So if we're thinking about second derivative, there's a second derivative test. Second derivative test says if my second derivative is positive, my curve looks like this. If my second derivative is negative, my curve looks like that. And if my second derivative is 0, I have no idea what's going on. So if I want to be a local maxima, I need to have the second derivative needs to be negative. So any place where the second derivative is positive is automatically cannot be a local maxima. Now you might say, does that prove it's a local maxima? And the answer is, well, we don't know. It would depend on what happens with f prime of x, and we don't have enough information to find f prime of x, and we definitely don't have enough ability to integrate this. So we'll never know what f prime of x is. But again, we just need to know what can it be. So what we're going to do is we're going to plug these values in. Notice this part. This is always positive because e to anything is positive. So what I'm really going to be looking at is x minus 5 over x plus 1. And I'm looking for any time when I'd end up with a negative number. So plug in negative 2. Minus 2 minus 5 is negative. Minus 2 plus 1 is negative. That's two negatives. That becomes a positive. 0. Minus 5 over 1. That's negative. Well, if it's negative, it could work on our list. 2. That would be 2 minus 5 is minus 3. 2 plus 1 is 3. That's a negative over a positive. Works. Could be. Could be. 4 minus 5, negative. 4 plus 1, positive. Negative over positive. Well, that could be a max. Could be. 6. 6 minus 5, positive. 6 plus 1, negative. 6 plus 1, positive. Positive over positive is positive. So, 0, 2, 4. They can be local maxima. We just don't know if they are. And that's okay. That's not what we're asked. Just what can be. All right, number 13. How are you doing? Doing okay? You can take a break, by the way, or we can just keep going. Let's keep going. Let's do it. We can make it. Use Newton's method to approximate a root of the function f of x equals x cubed minus 6x squared plus 5x plus 8, where x0 equals 1 is our initial guess, and we're asked to find x2. Now notice this is not a multiple choice. Submit answer as a number. So we get to do numbers. Woohoo! And whenever we have a number, we'll round it to the nearest hundredth. Now, spoiler. If you're asked to find a number on the exam, it's going to be a nice number. So, if you're not getting nice numbers, well, check your work. Check your work. Now, the key to Newton's method is to remember the basic rule. It says, look, I'm going to make a series of guesses which get better and better. It's, every guess I make is better than the guess I made before. And your rule is, you take your current guess, subtract the function at your current guess over the derivative at your current guess. And if you do this often enough, then lo and behold, you'll get better and better results. So, what do we have? Well, so our current guess, our initial guess is 1. So our next guess would be what? Well, you take the previous guess, which is 1, subtract, plug 1 into your function. Okay, so that's 1 minus 6 plus 5 plus 8. Divide that by the derivative. Oh, okay, we've got to plug f prime of x is what? 3x squared minus 12x plus 5. So, that's 3 minus 12 plus 5. Okay, now we want to simplify this because we have to submit an answer. So we got to think about this. So 1 plus 5 is 6 minus 6. These three terms will all cancel each other out. So what do we have? We have 1 minus 8 upstairs. Then we have 3 plus 5. That's 8. Minus 12 is minus 4. Minus minus makes a plus. 1 plus 8 fourths. That's really 1 plus 2, also known as 3. All right, that's not our answer, right? Because that's x1. So 1 to 3. Now, don't guess. Work it out. x2. Well, plug it in, right? So the previous guess, 3. Minus, and I'll actually write this down, f of 3 over f prime of 3, just so we know what we're doing. So that's 3 minus, okay, f of 3. So 3 cubed is 27. 6 times 9, 54. 5 times 3, 15. 8, well that's 8. All right. Plug in 3 here. 3 times 3 squared, 27. 12 times 3, 36. 5. All right, 5 wasn't very exciting, but all right. Let's see. 27 plus 5 is 32. 32 subtract 36. That would make it negative 4 downstairs. Oh, that's interesting. Same as what we had there. Well, coincidence, right? Don't read too much into these things. How about upstairs? Well, let's do the pluses first. 27 plus 15 would be 42, plus 8 would be 50. Subtract 54, makes it -4 upstairs. Well, that means it's really 3 minus 1, which is 2. So what's our answer? Well, we need to take this number 2 and round it to the nearest hundredth. So 2.00. You could have just entered in 2, by the way. That would be sufficient. But that's the answer. Woohoo! New 10. New 10. Number 14. Approximate the area under the curve y equals x squared plus x over 4 from 0 to 8 using a Riemann sum with the interval split into 4 equally sized parts and using the left endpoint in each part. Now, follow the instructions. You could say, hey, I'll just find the area. That's even better. But the instructions don't say to find it. The instructions say to approximate it. We want the points. In fact, we want all the points. So we're going to follow all the instructions. So we're not going to find the area. We're going to approximate the area. So how do we go about doing that? Well, we think about what are we doing? We're going from 0 to 8. So I'm going to draw my line 0 to 8. I need to split into 4 parts. So if you go halfway and then halfway again, that gives you 4. Okay, so there's our parts. They're equal, so that's good. What are our widths? Well, they're all 2. We can spot that. That's easy enough. Okay, now Riemann sum, it's the sum of the value of the function times your width. So delta is your width. We often think of delta as being used for change, and you can think of that, well, as I was going to say width, and we already used the word width, and you think of the value of the function as like the height. So what's happening is you're really approximating a rectangle, and then you're adding them up. Okay, now we just have to pay attention. It tells us where to pick our points. And this says the left. Okay, what does that mean? Well, that says for each interval, I go to the left, to the left. When we make a choice, we choose to the left. You must learn this by now. Calculus can be fun somehow. You'll get an A in the class, and then you will go to Calc 2 and have a blast. Woo! To the left, to the left. All right. Okay, so again, value of 0 times the width, f of 0 times 2, f of 2 times 2, f of 4 times 2, f of 6 times 2. So the last thing to do is to find these values. Plug in 0. 0 plus 0 over 4. Well, that's 0 times 2. Plug in 2. 4 plus 2 over 4. Now, 4 plus 2 over 4, well, that's really 6 over 4 times 2. Plug in 4. 4 squared. And 7 years ago. No. 4 squared is 16. Plus 4 is 20. Divided by 4. Well, that's actually 5 times 2. F of 6. 36 plus 6. That's 42. The answer to life, the universe, everything. So 42 fourths times 2. Let's clean this up. Really, this is 12. Okay, so 0, 12 fourths, 3, 5 times 2, 10. 42 times 2 is 84. 84 divided by 4 is 21. So 3 plus 10 plus 21 gets us up to 44, right? No. I'm distracted just because of the 42. It's such a great number. Beautiful number. All right, here we go. Serious this time. 3 plus 10 is 13, plus 21 makes 34. And nearest to 100th, so we can make it 34.00. But again, numbers that aren't so bad. Numbers that we can work with. We can work with these numbers. Good. Given the separable differential equation, now that's not the differential equation, just looks scary. And that y equals 2 when x equals 1, find the value of y when x equals negative 1. Now, I'll tell you at the start, this looks really, really scary, actually. I'll be honest with you. But it's actually, among separable differential equations, it's kind of the easiest kind of separable differential equation. Because notice what's not there. This is a separable differential equation where there's not much separation to go on. Because if you look here, there's no y. Now, oftentimes there will be a y, so be careful, be ready. There might be another problem on the exam involving separable differential equations, and there will be a y, so know what to do. But here, what can we do? Well, let's move things across. So e to the x over x cubed dy dx is equal to this stuff. Now let's pull out what's in common. Upstairs, they both have 2e to the x. Downstairs, there's 2x cubed. And then what's left? Well, there's an x cubed minus 1. Yeah, there is. It's true. All of it's true. The 2's cancel. E to the x's from both sides cancel. The x cubes from both sides cancel. And you can even do the following. Look, I'll move the dx across. dy equals x cubed minus 1 dx. And now we're like, cool, we've separated. We have all the y's on one side, all the x's on the other side. Again, this is an easy case when it's just dy. Usually we have something slightly more interesting. Integrate. Y equals 1/4 x to the 4th minus x plus c. Now, we have initial condition. We may or may not, but here we do. Let's see. It says when you plug in x equals 1, you get y equals 2. So 2, that's y, equals a 4th times 1 to the 4th, which is a 4th, minus 1 plus c. Okay, so, well, what can we do here? Well, we can make this 2 plus 1 minus a 4th equals c. Well, 2 plus 1 is 3, minus a 4th, that's 12/4, minus 1/4, that's 11/4. Yes? All right, so we have our function. Y equals 1/4 x to the 4th minus x plus 11/4. Now, plug in negative 1. So, what happens? So, we get at x equals negative 1, we'll get y equals 1/4, which is that piece, minus a minus 1 plus an 11/4. So 1/4 plus 11/4 is 12/4, which is 3, minus 1 is plus 1, so this is really 3 plus 1, which is 4, and therefore C is our answer. All right, good. Next problem. Number 16. The graph of a function f of t defined on the interval -2 to 6 is shown below. Hey, the function, how are you? Now the curved part of the graph, that looks pretty curvy to me, is a half circle of radius 1 centered at 2, 2. So there's the center. Okay, good. Find the integral from 1 to 6 of the absolute value of f of t dt. So, notice there's an absolute value. That says that really anything that's negative flips up. Okay, so we'll fix our picture here. All right, so there's our absolute value. And we're told we're going from negative 1, sorry, not from negative 1 to positive 1 to 6. So here's positive 1, here's 6. So we're looking for this area here. Now, instead of trying to do the function, let's think of the geometry. So what can we do? Well, we can make some pieces here. There's a circle. Now what is that? Well, that's half of a circle. So you can imagine filling it out all the way. So half of a circle of radius 1. So 1/2 times pi times 1 squared. So our answer should have a half pi. Well, that knocks out a couple choices. Now how about the other piece as well? I can take this triangle and I can actually put it and fill it into here, and that would give us a 2 by, what is it, 1, 2, 3, 4. So that's 2 by 4, which is 8. So we should have pi over 2 plus 8. And that's the answer. And we're done. Woohoo! Cool. I almost feel like I need to pause for a second because it feels like, really? Can the problems on the test be this easy? And I'm going to tell you right now, because if you're listening, you deserve to hear stuff like this. We didn't pick the hard problems for the exam, and we didn't pick all the easy problems for the exam either. We picked the best problems. Some of the problems on the exam are going to be very quick. If you know what you're doing, they're going to just flow out. And others will get you to stop and think for a little bit, but nothing was chosen where I said, we really need to punish the people. We're not about punishing. That's not our style. That's not our style. Number 17. Find the integral from pi halves to 2 pi of sine of x times sine of cosine of x dx. Now, the part that seems very strange here is sine of cosine of x. That's weird, because we have a function in a function. So when you see function in a function, what do you think of? If you're taking derivatives, you think chain rule. If you're taking antiderivatives or integration, you think substitution rule. So, what do? Well, substitution, it's an inside job. So we say, all right, we're going to let our cosine of x be our inside function. So derivative of cosine, du, is negative sine. All right, so we got a sine, so I'm just going to move this negative across. So we say, okay, aha, good news. So this will become what? Well, minus, coming from here, sine of u du. What about the bounds? Is it still pi over 2 to 2 pi? Why not? Well, be careful, right? Got to plug in your bounds. Because these are x bounds. We need to be to u bounds. So, pi over 2. Cosine of pi over 2? 0. Cosine of 2 pi. That means you've come full circle back to where you started. And cosine of 0 is 1. So, integral of sine. What's the antiderivative of sine? Well, the antiderivative of sine is minus cosine. So minus cosine. It's kind of weird, right? The derivative of sine is positive cosine, antiderivative negative cosine. It's almost like they want you to not pay attention and make a mistake, but we're not going to let them do that to us. We're going to get all the points. All right, so we're going to get cosine of 1, subtract cosine of 0. Well, that's not one of our options. But certainly the sine of 1, those are out. Wait a second, cosine of 0, what is that? That's 1. So we should have cosine of 1 minus 1, and that is an option. So there we go. B. Woohoo! We got it. All right. Number 18. Find the integral from 0 to 2 of the square root of 4 minus x squared. What's the antiderivative? You're right. I don't know that one either. Can we do this one? Maybe. Maybe not. No. There's no maybe. Of course we can do it. We'd never be asked to do something we can't do. Well, let's think about the picture. First thing is, I should have added that there's a dx there. We'll fix that in post-production. But what do we have? Well, we can say, look, this is a circle. See, y equals the square root of 4 minus x. Whenever you see like square root of number minus something squared, you should be thinking circle. And so, for example, y squared equals 4 minus x squared, or x squared plus y squared equals 4. So it's part of a circle radius 2 centered at the origin. Now which part? It's the top part. In fact, we only want to have the y positive, because that says y positive, and we want x from 0 to 2, which means it's a quarter of our circle radius 2. So 1/4 area of a circle radius 2 is pi r squared. Pi. So that's the answer. Cool. Nice. Nice, 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 nice. All right. We're doing great. We're like 75% of the way through. Number 19. Use the linearization of f of x equals the fourth root of x at x equals 625 to find an estimate for the fourth root of 610. So linearization is just a fancy way of saying tangent line. All right, cool. So what do we do? Well, we're going to find our tangent line. So we should make some notes here. We have f of x is x to 1/4. F prime of x is 1/4 x to minus 3/4, which is really 1/4 times x to 3/4. Now, we plug in our 625. So f of 625, 625 to the 1/4. Now, of course, that wasn't chosen at random. 625 has to have a nice fourth root. Probably should have a 5 in it. In fact, it should be 5. This is a place where you could use your calculator if you weren't sure. How about f prime of 625? Well, that's 1/4 times 625 to the 3/4. But look, we already know what the fourth root of 625 is. That's 1/4 times 5 cubed. Oh, what's 5 cubed? 5 times 5 is 25 times another 5 is 125. And so if you multiply this out, this becomes 500. So 1/500th. Now, our tangent line, f of a plus f prime of a, x minus a. This is good to know. So remember this, tangent line. All right. So now, what can we do? Well, what we can do here is we plug it in. So we're going to get 5 plus 1/500 times x minus a is the 625. All right. So, well, what happens next? Well, now we've done the linearization. Now we've got to use it. So, the fourth root of 610, that's f of 610. That's approximately, what happens when we plug 610 into here? 5 plus 1/500, 610 minus 625. Well, that's 5 plus 1/500. 610 subtract 625 is negative 15. Now, 515 have a common factor of 5. So 5 minus, and if you take the 5's out, 3/100, well, that's really like 5 minus 0.03, which is 4.97. There's our answer. Now, you might say, hey, I have an idea. I'll just pull up my calculator, because the calculators are allowed, and I'll take the fourth root of 610. And whatever is the closest, that's the one I'll pick. Now, it turns out the fourth root of 610 is really, really close to 4.97. So you're probably thinking, cool, I should use that strategy. But I'm going to tell you right now, beware. And when I say beware, here I'm using the word wary because it makes me sound very sophisticated, like, ooh, he knows how to use different vowels. You might just say, why don't I just find the exact value, whichever one is closest, that's the one I'll get. Well, remember, we're after an estimate doing a certain procedure. And sometimes the estimate is not always very close to the exact value, because for whatever reason, we might be far away from our point of tangency. We might need additional information. So don't rely on the true answer to help pick one of the guesses here. Use the process, because we can do something, and we've done it in the past, where we have it, where the true answer is far enough off from the approximation that you'd be led astray. So, all right, just word of warning for those who are still here. I hope you're still here. We're in our home stretch, right? We're into the 20s now. Okay. Given that for a particular value of b, the function f of x equals e to the bx over x squared plus 4 has a critical point at 1, find the value of b and the intervals where the function is decreasing. Well, critical points, almost always the way we do that is we think of derivatives. So let's take our derivative. So quotient rule. So we're going to take the bottom times the root of the top, b e to the bx, minus the top times the root of the bottom, all over the bottom term squared. Now, that's our derivative. What do we know? We know we have a critical point at 1. So that says plug in a 1, something interesting is going to happen. Well, it's not going to be undefined. So what has to happen is at x equals 1, the numerator has to equal 0. So 5 times b times e to the b minus e to the b times 2. So I've just plugged in x equals 1, cleaned it up, has to equal 0. E to the b's you can divide out. 5b equals 2, b equals 2/5. That lets us rule out c and d. Now we can think about, all right, well, what's true? Okay, are we increasing or decreasing on these intervals? Well, actually, we can answer those questions pretty quickly, right? All I have to do is pick some values. So for instance, let's pick the value of 0, right? What happens when I plug 0 in? See, 0 is a nice number. If you plug 0 in here, you get 0. Plug 0 downstairs, you get a positive. B is positive, we just saw that, and that's positive. So we know that f prime of 0 is positive. Well, that says we're increasing on 0. So, all right, well, that says we're definitely increasing on 0. That's a good candidate. Well, how about from 1 to 4? Plug in another number. Let's plug in, say, 2. Well, 2 squared plus 4, that's 8. B is 2/5. And then we have e to the 2b. And I know you're like saying, but see, we know b. Yeah, whatever. Minus e to the 2b times 4. Right? Because we're plugging in x equals 2. 2 times 2 is 4. What do you get here? Well, if you pull out the e to the 2b, whoops, e to the 2b, 16/5 minus 4. Which one's bigger? Well, it turns out 16/5 is 3 1/5. Minus 4 means it's negative, which means the derivative at 2 is negative, which means we're not increasing, we're decreasing. So that's definitely ruled out. So that's our option. We're going with option B. All right, number 21. Given the graph of the derivative as below on the left, so this is our derivative, match the graph of the function on the right. It's a little bit hard to read, but hopefully I'll point out this says f1, f2, f3, f4. So what are some things? So this is our derivative, right? So here's our f prime. Now, what you should notice is that you have 3 places where the derivative equals 0. So we should be looking for 3 places which have a flat tangent line. So that one has only 1. That one has 1. That one has 1, 2, 3, 4. It looks like maybe in a 5th. That one has 3. Good enough for me. That rules all the others out. So it's f4. Now you can do other things as well. You can say, hey, look, it's going to be decreasing, increasing, decreasing, increasing. Because look at the sign. Negative sign, positive sign, negative sign, positive sign. So I want to go down, up, down, up. See, this goes down, up, up. This goes up, down, up, down, up. This one down, up. Again, matches. You don't have to match every detail. You just have to have enough to get it right. Now, be careful. Be careful. It says match the graph of a function. Is it true that if you have the derivative, there's only one function it can match? And why not? Well, it's not true. And the reason why not is because it might be the case that you can shift. So be careful. Be the right amount of careful. Number 22. Determine the function f of x given that our derivative is 12x squared plus e to the x minus c, and f of 1 is 4 plus c. All right. Well, we can actually rule out a couple of things. Notice, when I plug in 1, I need to get 4 plus e. So let's see. Plug in 1. 24 plus e. Nope. Can't be that one. Plug in 1. 4, that's good, plus e minus e. Well, that's just 4. Nope. How about this one? 4 plus e minus e plus e. Maybe. Could be. How about here? 4 plus e minus e plus 4. That would be 8. Nope. So there's our answer. And you're probably saying, what? You didn't even do anything. No, I did something. See, I knew my answer had to have the case that when I plugged in 1, I got 4 plus e. And that's oftentimes enough. So remember, your goal is to figure out what the answer is. And in multiple choice, you can do that by saying, what is the answer not? Now, suppose we were doing it the normal way. Well, take the antiderivative. So, integrate term by term. The integral of 12x squared, well, add 1. That would be x cubed. And divide by 3, so 4x cubed. Integral of e to the x is e to the x. Integral of e, well, remember, e is just a number. I know it has special significance in certain settings, but for right now, it's just a constant. So it's that constant times x plus c. And now, what do we need? Well, plug in 1. What is f of 1? It's 4 plus e minus e plus c. And it has to equal 4 plus e, because that's the rule. The e's here cancel, the 4's there cancel, and indeed c equals e, which means that we were correct. But again, use the power. There's actually a lot of fun things you can do with a multiple choice test to help you get to the answer a little bit faster. So you might as well enjoy it while you can. All right. Given that our function has this crazy looking expression, what is the 50th derivative? Wow. Now, what is it we're not going to do? What we're not going to do is write down 50 derivatives, because that's going to take too long. And probably don't even want to plug it into a computer, because it may not write it in a compressed way. This 50 factorial, remember, what, by the way, in case you forgot what the factorial means, that means you start at whatever number is, so for example 50, and then you multiply it by 49, then multiply that by 48, and you keep going until you get all the way back to 1. All right, so that's a huge number, and a computer would probably write it all out. And you'd be like, that's too much information. Okay, here's the fun thing, is powers of x are easy to take derivatives. Because what happens is you say, look, this is x to the 1, and every time you take a derivative, the power decreases by 1, and then if it ever gets to 0, the next time it goes away. Well, I'm going to take 50 derivatives, so this term is going to go away. Here I have 30 derivatives. So after 30 derivatives, the power will go to 0, and then after that, it's going to be gone. So this one's going to go away. 50 derivatives. Well, that will get us down to x to 0, so it's going to be a number. But what's going to be happening is every time I take a derivative, the exponent comes down. So it's first going to be 50, and 49, 48, da-da-da, until we get down to 50 factorial. Right? So there should be a 50 factorial. There's no 50 factorial in the first one. The 30 factorial would be if I had brought those down, but that's just going to be completely gone. So these two are out. So we've narrowed it down to D and E. Now, what happens? Well, the 3, every time we take the derivative of this part, there's going to be a 3 coming out, so it should have a 3 to the 50th, so that's fine. Now the question is sine or cosine? Well, if I start with sine, the derivative of sine would be cosine. Derivative of cosine, negative sine. Derivative of negative sine is negative cosine. And then it keeps cycling. Sine, cosine, negative cosine, dot, 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 dot. So it does this every 4. So how should I think of 50? Well, 50, if I'm thinking in terms of steps of 4, it's like I took 4 times 12 plus 2 more. So if I'm taking 50 steps, in essence, if I cycle every 4, it's like I took 2, which means we should be looking for something with a negative sign involved. So that means it's D is our answer. All right. 24. Find all C satisfying the mean value theorem for derivatives for the function f of x equals 4x cubed plus 2 for the interval from 0 to 1. Okay, well, mean value theorem for derivatives means what? Well, it says that the mean value, something about average value. So the derivative at some point is equal to the average rate of change, f of b minus f of a over b minus a. Now in our case, that's going to be f of 1 minus f of 0 over 1 minus 0, because we're going from 0 to 1. There's our a, b. Plug in 1. 4 plus 2 is 6. Plug in 0, 2. 1 minus 0 equals 4. So I want some place where the derivative equals 4. All right, so what's the derivative? Well, f prime of x is 12x squared. 3 comes down, and drop the power, and 2 goes away. So 12c squared, because I'm plugging c into the derivative, equals 4. C squared equals 1/3. So that says c needs to be plus or minus 1 over square root of 3. Aha! Cool. Now look, there's a minus 1 over square root of 3, a plus 1 over square root of 3, and a both. Which one do we pick? But remember, what does the mean value theorem say? It says, yes, there is a c, and it's in the right range. Our answer has to be from 0 to 1. And so once we know our answer has to be from 0 to 1, for free, we knock out anything with a negative answer or anything bigger than 1. In fact, the mean value theorem says it can't even include the endpoints. So if we just remember that it has to be between 0 to 1, we can skip all the work and jump right to the answer. 1 over the square root of 3. All right, 24 problems. And we didn't go super fast, and it didn't take us too long. So hopefully the exam should be fine. Because remember, we picked sort of the better problems for the exam. Not harder, better. You can do it. You can do it. We want you to do well. And good luck. This is our sort of our farewell message, I guess, this exam. And we're going to send you off with lots of love. All right. Take care. Bye.